Hello everyone, and welcome to the Unit 4 review for Geometry B. In this unit we talked about transformations. I really love this unit because it does something very visual, something that you can imagine using in your real life. We mainly talked about these four transformations: reflections or flips, rotations or turns, translations or slides, and dilations, which are enlargements or compressions. Let's talk about one type of vocabulary that has to do with the transformations we talked about. We talked about two different kinds. One is called an isometry. An isometry uses rigid motion. That means that the figure maintains its same size and same orientation as it changes, but it can change location. Three of the transformations that we're talking about are isometries: the translations, the reflections, and the rotations. When we get to dilations, those are not considered isometries because the size changes. One of the ways we talk about transformations is by using the A, or any letter, and that represents the original image. Once the change or transformation has taken place, we use A prime to talk about the image. So don't get confused when you're asked to ask for the pre-image or you're asked for the image. Remember, one is just the original location and one is the new location, and the prime just represents the second one. So for instance, we have a triangle here, XYZ, and it could be translated to triangle X prime, Y prime, Z prime. All of the vertices, the whole shape, the whole triangle will be slid in the same direction, the same distance, so that the shape and orientation are identical afterwards in the image. Now, in a translation, a lot of times you'll see this type of nomenclature. If it's going to change, we refer to the coordinate plane, and in this case, a translation represented by the capital T of points X, Y will transfer to 5 more than X, 2 more than Y, meaning that the pre-image is going to move 5 spaces to the right and 2 spaces up. So if I had this point on my graph, -1, 1, and I wanted to change it X plus 5, Y plus 2, I'd move 5 spaces to the right. Then I would turn and go 2 spaces up, and my new location, my image, would be 0.43. We also talked about some inverse translations. An inverse translation takes you backwards. So if I started here at my 0.43 and I did an inverse operation of X plus 5, Y plus 2, I would go in the negative direction, or left 5, and just reverse what the instructions are, and then down 2 instead of up 2, and I would return to my original point of -1, 1. Now, this one has a little negative sign, which means it's an inverse translation, but you'll notice that it has a 2. That means that not only are you going to do it backwards, but you're going to do it twice the distance. So in this case, my points X and Y that are going to be transferred X plus 3, Y plus 2, as a double inverse, it's actually going to go X minus 6, which is twice X minus 3, and Y minus 4, which is twice Y minus 2. So not only is it the inverse, but it also is twice as far. The next isometry we talked about are reflections. Reflections are usually given the line across which the reflection will happen. The easy way to do this is in graphing, where you look at the line, you count the number of spaces to the line, count the same number of spaces to the other side, and place your new mark, whether it's a point or a shape. Sometimes we call a reflection a flip, and everything will look to be in a mirror image. Sometimes they give you a line K, they might give you the equation for the line, or they might have you reflecting something across the axis. Let's say that they gave you the point 2, 3, and the image is negative 2, 3. So we started out at 2, 3 right here on our graph, and we're going to go to negative 2, 3. And they say it was a reflection. What line did we reflect across? Well, you can see that the y-axis is exactly between the 2 points. If you move 2 spaces to the line, 2 spaces in the opposite direction, you would get to your reflected point of negative 2, 3. So this is a reflection over the y-axis. What about this nomenclature? It has reflection, but it has a little x. That means you're going to be reflecting across the x-axis, and you're going to be starting with the point 2, 5. And I'll just graph that in a different color up here. 2, 5. Reflected across the x-axis, if I count down 5 spaces to the x-axis, I'll keep moving in the same direction 5 more spaces and get to my new point at 2, negative 5. And there it is right there. Now, sometimes we have a composite reflection. You can have a composite including any number of transformations, but they have to be done in the order that are given. And they're usually represented by a solid dot or an open dot in between the transformations. This can be read as after. So remember, when you see this, you're always going to be doing the last transformation listed first, because the first one is going to be reflected, in this case, over line N, after it's reflected over line M. So this is an example from your test where they give you a picture of a fighter jet, and they want to know, what does it look like after it reflects across a line? Well, we reflected across line M first, and it's going to look like the exact mirror image of that jet. Then once it's reflected across M, it's reflected again across N, and it's the mirror image again. Notice that the final image is exactly the same as the pre-image. Another isometry we talked about was rotation. A rotation is given by telling you that a certain point or a certain shape is going to be reflected about a certain point. That's going to be the center, as if it were a circle. And it's going to give you a number of degrees that you're going to rotate it in the counterclockwise direction. Remember, if they don't give you a direction to rotate, it will always be counterclockwise. And the nomenclature looks a little like this. We've got RO 180. That means that it's a rotation around the origin of 180 degrees. Well, 180 degrees is a half of a circle. So this can also be written as a HO, which is a half turn around the origin. And a half turn around the origin is pretty easy to calculate because it just reverses the signs of both the X and the Y coordinate. If a figure is rotated 180 degrees around the origin, it would be the same as if it were rotated negative 180 degrees, which would rotate clockwise. So if you see a negative number of degrees, that's going to go in the opposite direction, or clockwise. But it doesn't matter. If you're going halfway around, it doesn't matter whether you went clockwise or counterclockwise. In this example, the figure shows a rotation about the origin of 90 degrees of the point P, which is currently at 2, 5. So it's rotated 90 degrees about the origin in the counterclockwise direction. Where will the image be? Well, you'll see that what I use as a technique is to draw a line from the origin to the point and draw a line perpendicular to it in the counterclockwise direction, and at the end, at the same distance, you will be able to put your new point P, or P prime. The original point was 2, 5, and the image point is at -5, 2. So you probably remember from your lesson there was a little chart that they created how you can change your X and Y values depending on the degree of rotation. That's not something you have to memorize, but if you have it in your notes, it can be very helpful. Composite transformations might involve more than one, and we talked about that already with the jet airplane. If it's a rotation, it might be a combination of more than one rotation. And in this example, it's not going to be rotated about the same point. If O is the origin and P is the point 43 that I've got right here on the graph, find HP after HO of 30. Okay, what does that mean? Well, we're going to be doing a half turn around point P after a half turn around the origin starting at the point 30. So we're going to do this in 2 steps. First, we're going to do a half turn around the origin, and I've kind of drawn that for you. Here's our original point down here at 30. If we are doing a 180-degree turn, that's basically the same as a reflection. I'm going to go counterclockwise around 180 degrees, and I'm going to end here at -30. And whenever you do a 180 degree or a half turn around the origin, remember your x, y values are going to switch to -x, -y. Next, we're going to do a half turn from the new image around point P. So I've drawn this yellow line for you. I've drawn a line from my new image up to point P, which is right here. And then I've continued in the same direction, the same distance up to a point up here, which would eventually turn out to be 11, 6. And again, if you've got copied into your notes how you can calculate the term or the coordinates of a point after a half turn, then that'll save you a little bit of work. But looking at on the graph, you can see how you can logically get to the point that's a half turn away. Now, sometimes we have a rotation that is a composite as well. The rotation R, now remember, there are a couple of different symbols. One is a capital R that's pretty plain. That stands for reflection. The fancy R that you're going to be seeing is a rotation. Now, a rotation, like we just did, is going to be around a certain point. Sometimes a whole shape can rotate. And in this case, this rotation maps all of the points 60 degrees about the center of a regular hexagon. So where will the B move for R2? Now this 2 isn't down below like we've been seeing some of the nomenclature, but this one was more like the twice times the inverse rotation or reflection. This one is going to be done twice. So I'm going to start at B, which is right up here, and I'm going to rotate 60 degrees, which is one space, over to A, and remember I'm going counterclockwise, but it says I need to do it 2, so I'm going to do it one more time, and I'm going to get down here to point F. Remember, each one of the central angles in a hexagon is 60 degrees. So by doing this 2 times, I'm going a total of 120 degrees, and that will put me basically in the space of 2 vertices away from where I started. Now, as I said before, a dilation is not an isometry, but it's still a transformation. It changes the size of the figure, so it's not actually rigid motion. It can be represented as a figure that's getting larger, enlarging, or contracting. Now, the nomenclature for this is a capital D, and it always has 2 indications after it. What is the point or the center of dilation? and what is the scale factor of dilation? So how much bigger is it going to get? And where is it going to be expanding from? So if you had a dilation that went from 0.50 and it got all the way to 10,0, what was the scale factor? Well, assuming that it started at the origin, all you have to do is multiply both your x and y by the scale factor, and you'll get to your image. Well, what did we multiply 5 by to get to 10? We multiplied by 2. And we would have to do, of course, the same to the y, but 0 times 2 remains 0. So the scale factor, or k in this case, was 2. Remember that positive scale factors, anything greater than 1 is going to make an enlargement. A fractional scale factor will be a contraction. It will get much smaller. You can also do an inverse dilation. In inverse dilation, you would do mathematically the same way, but you might be amazed to see that it will flip your shape inside out or backwards. The identity dilation is a special case where the scale factor is 1. Well, I said if it's greater than 1, it's an enlargement. If it's a fraction or less than 1, it's going to be a contraction. But if it's 1, it will stay exactly the same. In this example, if you had the 0.40 and it was going to be dilated from the origin on a scale of 1, it would still remain at 40. Now, when I talk about dilations, I did tell you that the shape would be the same, but it would just be larger or smaller. And I also told you that the proportions of the sides would be the same. So it's worth noting here how to calculate what the lengths of those sides would be. So here they ask you, what is the value of x? We've got two triangles. They don't tell us that the triangles are similar, but you can see that one of the angles matches the other angle in the other triangle. F goes with P. And then angle G is the same as angle Q. Well, we know that if two of the angles are the same, the other one can be calculated and it's going to end up being the same as well. So we could mark angle D as corresponding to angle R with 3 angle measures. And now we know that these are similar because all 3 angles are the same. The size obviously is not the same, and in this image they don't even look to be the same shape, but we know that they are. We just have to figure out which side goes with which side because we want to set up X with its corresponding side. Now X is between F and G, and I said that F corresponds with P and G corresponds with Q. So the corresponding side to X is going to be this side that's equal to 5. So I've set up a little ratio here of X over 5. And I want to find another set of corresponding sides that have values so that I can figure out the value of X. So I've chosen this FD side, which is 10, and it corresponds to side RP, which is 8. So I've set this up as 10 over 8. Now make sure that you do these in the same order. I had X on top from the FGD triangle over the PQR triangle, and I want to keep the same order from the DFG triangle to the PQR triangle. Both would be on the bottom. So once we set up two ratios that are equal to each other, that is called a proportion, and I know that the cross products are equal in a proportion. So I'm going to multiply 10 times 5 and set it equal to 8 times x, and then I'm just going to solve it. 10 times 5 is 50, and 50 equals 8x. To solve for x, I'll just divide, and I end up with 50 over 8. That can be reduced down to 25 over 4, and if I wanted to see it like these others, which are all whole numbers, it would be 6 1/4. I like to do that because I want to make sure that it turns out to be somewhat a reasonable answer. If it came out to be, 20 or something, I'd be a little bit concerned, because you can see that in the PQR triangle, 5 is the middle-sized leg of the triangle, and it should be the same in the corresponding triangle, between the longest and the shortest side. Finally, another thought about similar triangles. I told you that if all of the angles are the same, then we have similar triangles. Well, what if you're told that two triangles are similar, and you are told to find the measure of the angles of x, y, z? Well, it doesn't have any labeled, but because they told us that these were similar triangles, we know that they are corresponding. Not only that, we know that they are going to correspond in order. So angle N is going to correspond to angle Z. So I know that Z is going to be 50. Angle L is going to correspond, because it's the first letter in the triangle, is going to correspond with X. So X is going to be 62. Well, I don't have another angle measure down here for P. I know that it corresponds to angle Y, but in order to calculate it, I'll have to go back to what we learned a couple units ago, and that is that all of the angles of a triangle add up to 180. So I'm simply going to add the two that I know, 50 and 62. That gives me 112, and I'm going to subtract that from 180 to find the measure of the remaining angle. So that would be 8, and 7 minus 1 is 6. So that last angle is going to be 68 degrees. All right, that brings us to the end of our presentation. I hope that you were able to learn something, or maybe be reminded of something that you learned in this unit. I know it was a long unit. And if you were able to get some of this information down into your notes, I know that you will do better on that unit test. If you're still nervous or have some questions about what you're going to see on the test or what you'll be required to do, please save that question, and when you call me, which is a requirement for this assignment, you can ask me the question, or if you want to see something on the board, we can set up an extra review for you before you take the test. Thank you very much for coming in, and good luck on the test.